or the first part, so conduction is the movement of heat energy through solid objects in contact with each other. Okay? So it could be one solid substance, or it could be two substances that get pushed against each other. Or three substances that get pushed against each other. Right? Okay. Convection is the movement of heat energy in a fluid or a gas. Okay? And what causes convection goes back to relative density. This is why you had to understand relative density. That's one of the things it ties to. So we know that things that are hotter rise and things that are cooler fall, right? Like air. So that's one of the things that you got to understand. The relative density is what's causing what's called a convective current. The last one is radiation. Right? So transfer of heat energy through electromagnetic waves like sunlight. Okay? So let's take a look at conduction. Okay? So here's an example of taking a bar of metal and putting a heat source at one end of it. Okay? When you do that, so here's the heat source at this end, and here is the bar of metal. The molecules near the heat source start to vibrate, right? And so they're vibrating and they're like elbowing, and it's like a mosh pit thing going on, right? And they're kicking the crap out of the molecules next to them that in turn get agitated and start kicking the crap out of the ones next to them, and so on and so forth. And so the more they vibrate, right, the more it transfers the heat energy across. You notice that there's less vibration at this end and more vibration at that end, more little lines going around it. And remember, we said that everything has heat energy all the way down to absolute zero. Don't forget that. That was from lecture 1 or 2 on heat. Okay? So an iceberg has heat energy in it. Don't forget that. Okay? So this whole process of passing it along from one place to another, right, is conduction. And that could have been a bar of metal, right? And we could put a piece of concrete in direct contact with it. And so it's going to transfer across here, right? And then it's going to hit the concrete, and it's not going to go as fast because concrete is not as good a conductor as metal. Okay? In either case, molecule to molecule transferring heat energy. So you guys are familiar with this, okay? If I pick this thing up right here, this has a piece of wood on one side and a piece of metal on the other, and I put my hands on it, the piece of metal feels cooler than the wood. This thing's been sitting in here, this chunk, this is a piece of a window that's got aluminum on the outside and wood on the inside. This thing's been sitting in here for months. Right? This thing, I guarantee you, everything in this thing is at the same temperature, but yet this one feels cold and this one feels warm. Right? And that that deals with conduction. One is a better conductor than the other, so it sends the heat energy through faster than the other. Okay? And again, let's go back to the temperature. What do we say the temperature of the average human skin is? I wrote 86, but I don't remember if that's correct. Internal heat was 96.8, right? Or something like that, or was it 98.6? I don't know. But it's in the mid 90s somewhere, right? But your skin surface temperature, depending on where you take it, you know, under your arm, up your toe, whatever, right, is different. But skin, let's just assume that your skin temperature is at, let's say it's 86. I just took a guess at that, right? This stuff here is at whatever the temperature of this room is, which is probably about 70 degrees. Okay? So there's a delta T there, isn't there? What's the delta T? About 16 degrees. So heat is flowing from this object. Because remember, all objects have heat, even an iceberg. Okay? So the heat energy is flowing from this object into my hand. It goes faster here, and it goes slower here. Because this is wood and this is metal. Okay? And you guys are welcome to pass that sucker around and feel it. After a while, it's going to warm up to body temperature, so by the last people get it, they're going to go, hey, this thing feels warm. So, okay. Let's go to the next one, convection. So, convection is heat transfer in fluids and gases, and it generally takes place through a convective flow. Convective currents are set up in a fluid because the heat differential exists between one part of the fluid and another part of the fluid. All right? The hotter part of the fluid is lighter, so it goes up. The colder part is cooler, so it sinks down because it's denser, and the other part's warmer, right? So one of the things that I want you guys to understand is that there is a natural convective current, and then there's a forced convective current. When we blow air out of these ducts, we are forcing convection. Okay? All right. As an example of that, imagine taking a piece of water, putting it in a little ice cube, and putting it in the freezer and freezing it. And then take a warm cup of water, take the ice cube that's dyed, and drop it in the warm cup of water. The ice floats, but be careful because water is different than most substances, and so the reason it's floating is probably doesn't have something to do with its density. Okay? It has something to do with the hydrogen atom. So, but we'll ignore that right now. In either case, when this piece of ice begins to melt into water, right, that water is colder than the water that's around it, and so it starts to go down, right? And there's a certain level of delta T existing between the melting water and the water that I put it in, right? And so when a little bit of water comes off, that water immediately warms up and starts to flow sideways and mix in with the other. But as more and more of it begins to melt, right, the temperature differential between the warm water and the cold water is not as high, so it flows further and further and further. So after a while, the cold water is going to start flowing down, the warm water is going to rise, it's going to start to mix, and by the end of the time period of the day, the cup will no longer have any swirls in it at all. It'll all just be a lighter blue color. Because it slowly, through convection, became at thermal equilibrium. Okay? And then it's just all one consistent thing. Radiation. Radiation is the third method of heat transfer, and it is in the form of electromagnetic waves. An electromagnetic wave is basically it's sort of a sinusoidal oscillating electromagnetic field, okay, which means that there's two different things going on. There is an electric field and a magnetic field, all right? And they're traveling through space. Now remember, conduction requires one molecule to be touching another, and they're like having this fight because he's got more heat and he wants to give it to her, right? Or she's got more heat, she wants to give it to them, and they, send it on down. Fluid, there's still atoms and stuff in fluid, but what's happening there is the molecules and stuff are rising if they're hotter, and the portions of the material are rising that are hotter, and the other ones are colder, and as everything rubs, it just sort of sends across the heat energy. Radiation is different, because radiation will travel across a void. Is there any matter in space? Not really. I mean, there could be gases somewhere or something. Obviously, there's planets and asteroids and stuff like that. But in space itself, there's a vacuum. That means there's no substance. Electromagnetic waves will travel through a vacuum, through void. Is our atmosphere a void? It might seem like it because you can't see it, but it's not. It's full of oxygen and all sorts of other pollutants that we've put into the air. Okay? There's ozone up there, or there used to be ozone up there. There's all sorts of stuff in our atmosphere and our air. Okay, so this might seem kind of complicated to you, but you guys experience waves, electromagnetic waves, all the time. I'm sure you guys, even though you probably say you don't, you still listen to the radio periodically, right? And you watch TV, and that is radio waves going through the air and coming to your thing. You guys probably all use microwaves, and that's a form of electromagnetic radiation. You think it's magic? You think Harry Potter's sitting there going, waving his little wand and saying, "Get hot," every time you push the on button on a microwave? I don't think so. Something's happening, okay? We see light. Light's a visible form of electromagnetic radiation. If I stand here, I'm like blinded by that damn thing, okay? X-rays. You guys have all probably gone to the doctor and have had to get an X-ray. I had to get one recently after my little skateboarding incident. That wasn't fun, okay? Infrared rays. You guys will experience infrared rays. If you stick your hand in front of that projector, the heat that you feel is probably infrared. And you guys have probably gotten a sunburn at some point, and that was caused by ultraviolet rays. The only difference between all of these different things is the frequency, okay, of the wave. The frequency and intensity of the wave, okay? So here's kind of an example of a wave, right? And here you see a simplified singular version of a wave. Here you see one that's got two different sort of waves superimposed on a central axis, and here you see them in motion. Okay? So one of those and here we're not concerned with this, but just so that you know, one of them is, I think, an electrical wave, and the other one is a light wave. I don't remember. There's two different. What's that? Yeah, one of them is magnetic, the other one's electric, right?
No, magnetic.
Magnetic and electric, yeah. So, all right. So that's why it's called an electromagnetic wave. All right. Okay, I can go a little bit further because I think I'm almost done with this slideshow. So, another thing, 2 more terms to learn. Woohoo! God, you guys just gotta love this class, don't you? More terms to learn. Emissivity and absorption. Okay, absorption you probably know if you have a little sort of nephew that you've ever had to change his or her diapers. You put those very absorbent huggies on. But we're talking about heat energy, and so all substances that we come into contact with on Earth radiate. You guys are radiating right now. If your monitor is on and you touch it, it's radiating right now. Okay? Everything radiates. But what causes energy to flow from one thing to another is going to be the delta T, right? Yeah, not necessarily. Not with radiation. So, a measure of how much or well a substance radiates is called its emissivity. How much it emits. Okay? The measure of how much the substance will absorb radiation, or how well it absorbs radiation, is its absorption. Okay? Understand that the surface color of objects has a lot to do. The surface color and sheen. So by sheen I mean how shiny or dull it is. The surface color is whether it's a light color or a dark color. Has a lot to do with its emissivity and absorption. Okay? So I put together a little thing here. So we've got 4 containers. Shiny metal, dull black, and shiny black, right? So there's 4 containers. We fill them with hot water. We put them in the refrigerator. We've got probes inside of them. So the shiny container is going to be the warmest after 10 minutes. Okay? The dull black container is going to be the coldest after 10 minutes. All right? And that's because one of them has a higher level of absorptive quality and one of them has a higher level of emissivative qualities. Okay? All right. I think that's it. Escape and stop.